HFTO is high frequency torsional oscillation. There has been some kind of conjecture in the past. I mean, there's been a lot of disbelief sort of in the drilling industry in general about the existence of this. I think it's been generally accepted, 20 years ago, that vibrations generated in the drilling process are relatively low frequency. I mean, the drilling process itself is relatively low frequency. You might turn the drill string at somewhere between 120 and say 240 RPM, and that's only like 2 to 4 hertz. So when people start discussing high frequency torsional oscillations in the 50s or hundreds of hertz, there initially was some kind of disbelief, because well, that just can't happen. Nowadays, with the advent of more sophisticated sensors with higher sampling rates, it's been pretty much proven, without too much doubt, that it does exist. I think the evidence for it originally was, when you saw unexplained downhole failures, people would look at their equipment and look at the nature of the failure. And let's say it was a fatigue failure, the number of cycles required to cause that fatigue failure could not have been accumulated in the time of the run, of the downhole run, at the frequencies that people generally accepted occurred. So it was like a bit of a puzzle. Okay, we've got this many million stress cycles that have caused this failure, based on looking at the failed parts. That's pretty obvious. It just, you can see it. But the explanation is, okay, but it was only run for X amount of time, which, if it caused that number of stress cycles, they must have been in the hundreds of hertz. That's impossible. Well, now we know, that, through measurement, these high frequency oscillations can exist and do exist, and are very, very damaging. And one of the reasons they're very damaging is because of the high number of stress cycles. In order to cause something to fail in fatigue, generally you have to have a large number of stress cycles, fluctuations in stress. And, that can, if that occurs at high frequency, you can accumulate those stress cycles very quickly, and the component can fail, causing, very costly, downhole stoppages and stopping drilling, or even worse, leaving pieces of equipment in the hole. So the way that it's generally accepted that the high frequency oscillation gets generated is through the stick slip process. So a drill bit, when it takes a bite of the formation of the rock, it builds up torque, and a lot of the time it will actually stall and stop until the torque gets to a certain point where it can shear the rock, and that will take the drill string to wind up maybe several times. So you might find the bit stopping for several seconds, and then build up the torque to take that cut, and then it will release. And when it releases, there's a big impulse, a big input of rotational energy, and that's what can drive the torsional oscillations, these higher frequency oscillations of downhole equipment. The excitation is this impulse when the stick slip stall breaks. Well, there's been in recent years a big drive to sort of mitigate the high frequency torsional oscillation. Obviously, one of the drives is to prevent damage to equipment, or prevent, a slowdown in drilling effectively, because it's obviously a destructive phenomenon which slows down drilling and causes damage to equipment. So, people have been looking at this and have been focusing on research and development in this area. And the first stage of that has been almost kind of proving that it's there, that it exists. People have seen the twisted metal work and the damage it's caused, and, been struggling sometimes for an explanation. So, the first phase has been putting sensors into the hole that can measure this phenomenon, which means sensors with the right kind of sensing axis and type of sensors, but also the sampling frequency being high enough to pick up these higher frequency vibrations. So that's been the first stage, is measuring it to understand it better. And then the second stage really is, how do you stop it? It's not that easy. You've got a drilling process, which is at the end, a drill bit's at the end of a rather long drill string, and the drill string is the aspect ratio of like a human hair. So you can imagine it's quite limber in a rotational sense, and the drill bit quite regularly stops and stalls, and then it's release of energy as the drill string winds up. So, there's a focus in sort of detecting it, warning, the driller that this is happening, so they can take action. So in the drilling process, they can modify some of the parameters to see if they can reduce this phenomenon real time. So you might get the sensors that have been employed downhole sending a real-time warning to the surface. This is happening, this kind of severity, you need to do something to reduce it, and you can take some action at the surface. And the third area probably is, designing downhole tools that can actively, prevent or reduce the damage or the intensity of these oscillations. And I won't go into exactly what those tools do, but you can imagine what they're trying to do really is to either stop the stalling of the drill bit, or then to reduce the impact of the release, to then stop it from, creating these torsional oscillations. So that's kind of the third level of, technology and research and development that's going on. In order to understand this phenomenon better, a lot of work's gone into analysis and testing. From the analysis side, traditionally, engineers have been looking at the lower frequency end of the spectrum and probably ignoring the higher frequencies, because there wasn't a widespread acceptance that they could be excited. So now we understand they can be excited. The analysis side of things now looks at, torsional oscillation to higher frequencies than they looked at before. So before, you may have limited your analysis down to below 50 hertz. That's the kind of excitation you would expect. If you have any vibration modes in that area, you may be looking at seeing if you can get rid of them, or design them out, or take some steps. Whereas now that window is more like 500 hertz or even higher, where using analysis techniques, you would look at what torsional vibration modes there are in a drilling assembly, and really try to understand them. And the second step is in testing, where you could take models of the assembly and actually verify your mathematical models by testing scale models of a drill string to show that, okay, our analysis of this one case our mathematical analysis correlates well with the model testing, and so they can have a lot of confidence in then mathematically modeling lots of different cases. Okay, so you might verify one particular vibration case with the model to make sure that it's correct, and then you can then go and do a lot of changes to the model to see where the sensitivities are. And then lastly, we look at full scale testing. You can build up a BHA and actually drill rock and actually see some of those and record some of these phenomena occurring with a surface assembly. So, it's very difficult when you're downhole and you're like a mile into the Earth's crust to put sensors on a drill string and really get a good idea of what's happening. Of course, that's what we're about and that's what we do. But by the same token, doing a test is another valid way of doing it. And then you've got access to much wider spectrum of measurement techniques, and you can physically see what's happening. What's difficult to reproduce is the kind of torsional limberness of the drill string. It's like the aspect ratio of a human hair. So trying to do that at the surface is very difficult, but there are ways that you can adjust the boundary conditions of your tests in order to simulate that. Well, I see the main focus should be on prevention, really, preventing this from happening in the first place. Up until now, a lot of the developments have been really in terms of measuring the phenomena to understand it. But you've got two options really: prevent it from happening, or designing equipment to survive it. Obviously the most efficient thing to do is to stop it happening in the first place, because it's damaging. So you can make the tools, the equipment that goes down harder and harder and harder, and no doubt after we've finished talking about HFTO, there could well be another type of damaging phenomena that we haven't thought of yet, that is a consequence of designing the tools to survive HFTO. So I see the focus in the future being around preventing it in the first place. So we know that the energy that drives HFTO is from stick slip. So it seems perfectly logical that you would look at preventing that stick slip in the first place. Ways of doing that, keeping the bit moving, keeping it more efficient, and really trying to stop that bite, build up of energy in the drill string, and then release, and that's where the damage comes from. So I think we'll see people, companies looking at that and seeing how they can prevent that stalling of the drill bit and then that release of energy. So that's got to be the focus, really. Yeah, it's been it's been a journey, a very interesting journey. And initially, the way this all started was seeing damage to equipment that couldn't possibly be explained, by any other phenomena that we knew of at the time, or we knew existed. And so there was this kind of thinking about what could cause this, and the metalwork was telling you a story, and the story it was telling was, okay, there are a lot of stress cycles. The stresses are high. There's a lot of cycles, and looking at the damage, there had to be torsional vibration. It had to be, because that was the only thing that could explain say, for example, the directions of a crack or something like that. So then you're faced with this evidence that it has to be there, but there's also this denial, that those things, can't happen downhole. We can't get vibrations of those, magnitude and frequency. And so then there was this kind of theorizing about how you could excite that. And the theory, cropped up that, okay, with anything that can, excite that would be stick slip. But, at the time, as engineers, we faced quite a lot of pushback from, senior management and from customers saying, this can't exist. Show me some measurements. And of course, at the time, we didn't have any measurements because the instruments didn't, they couldn't capture information at that frequency. So, you were going there, the only evidence you had was the twisted metal. And it was hard to get that message across. And I think that's one of the reasons we had to go through this process of then creating sensors that could measure the phenomena and getting some belief. And we're kind of going over that acceptance curve now, from the sort of denial that this happened. Now into acceptance. Okay, it does exist. What are we going to do about it? And I think kind of that's where we are now.